we'll change gear a little bit again, talking about detection, and we'll go back to learning. And I mean, these are all learning, but I'm going to talk about now learning in a continual fashion. Now, why continual learning is so important? Turns out, I mean, when I was talking about training the networks earlier, I was talking about taking all the data. I might have data of cat, dogs, lions, trees, houses, and so on, and I all put them together into one data set, and I train the network, right? So in a batch mode. So rather than doing that, is it possible that I do some sort of a continual learning? We humans are really good at doing that, right? We learn something on day 1, and day 2 we learn something else, day 3 we learn something else, and we do not usually forget. We do forget. We selectively forget things, but we also not only learn to forget, but we also learn to learn in a continual fashion. So is it possible that I learn to learn in a continual fashion without forgetting what I've learned? Now, the standard deep learning is quite notorious in actually forgetting what you've learned, and I'm going to give you an example of such, the standard deep learning techniques, where I, for example, learn my task 1. Let's say the first time I take my network and I learn task 1, and that neural network task 1 is, let's say, to differentiate between a cat and a dog. Then what I end up doing is, after learning this, I learn task 2. And task 2 is learning between the bird and the flower. I, of course, add 2 separate neurons at the output, which are basically going to be the bird neuron and the flower neuron, along with the cat and the dog neuron. But unfortunately, if you do it this way, we're going to certainly learn bird and the flower, no question about it, but I might actually end up, I might actually end up forgetting my earlier things that I've learned. So now during test time, when I show bird, as an example, my brain says bird, and certainly my neural network also says bird. But when I show a dog, now I'm confused because I've forgotten what I learned for the bird. And why did I forget? That's the question. The reason why I forget, and it's called catastrophic forgetting, and the reason why I forget is because the way we've been learning. So if I now think about learning and look at the loss optimization landscape, which is plotted on the right side of it, and in terms of the gradient, if I look at things, the task 1 has been learned, and let's say the gradient directions for task 1 learning is G1, which is shown by the blue arrow. Now for G2, the second task, I might have learned in this direction G2, but what we have to be careful about is that, when I'm learning G2 or when I am learning a new task, there could be a maximum interference when I'm learning G2 if I learn in the direction which is shown in red, which is the opposite direction of G1, right? And it's possible because G1 has a component which is going in that direction. However, if I learn in the direction which is shown by this arrow, which is orthogonal to G1 now, I do not mess up the learnings that I earlier had. And by doing that, I may not have any catastrophic forgetting. So in other words, when I learn task 1, which is the first task, I learn it, and then I actually figure out the gradient direction for that learning. And the second thing that I do is that when I learn task 2, I actually learn in the orthogonal direction to G1. And if I'm able to do that, then I can do much better learning without forgetting what I actually learned earlier. So to that effect, actually, we propose what's called the gradient projection memory for continual learning. Why it's called gradient projection memory is going to be clear in just a minute. Again, the basic idea, when I learn task 1, I do the learning, and then I have to figure out the gradient directions. And it turns out that the gradient direction can be represented by basically, looking at the activation space of the input. So I basically look at the dog and the cat activation, and this activation is equivalent to the gradient direction, it turns out. So with that in mind, now if I take the important directions for G1, which is represented by looking at these activations and doing an SVD on it, really taking the most important components, SVD on it, and if I store it in a memory, I'm going to call it a gradient memory, then in that case, memory M, and if I store it and I don't want to mess up that particular direction, then of course I can learn. So to that effect, again, this is basically showing mathematically, I do the SVD on these representations and I store it in this memory M. The first time I do, the memory is empty. So after I've learned task 1, I actually come up with this memory M. If I now try to learn task 2, I have to add to that gradient memory, right, and learn. So to that effect, if that's the first learning that I do using GPM, now when I have a new input that comes in, remember what I have to do is look at the gradient space. And my gradient space basically is showing, and I'm showing at the bottom in the blue direction, that's basically the space that I have already learned. Some old information that I've learned. I'm showing it as a cartoon. Now, the new task that I have that comes in, I look at the gradient projection memory, GPM, and I decide that which direction the learning should be done. Right? Now remember that the blue portion that I'm showing on the right side of it, in the right corner, in the below right corner, where I'm showing is basically the learning for the old gradient. So the new gradient learning, if it is G new, which is shown in a direction which is not orthogonal to basically the old direction, then I actually project it in the orthogonal direction and do the learning, and I do not do any learning in the old direction, okay? Old learning direction. And that way, I do not mess up things. This actually does give good results, and the good thing about it is that I have least amount of forgetting. However, one of the problems of such learning is the fact that while it does a good job, beyond a certain point, you find that you have used up a lot of your gradient space, okay? So when I have to learn a lot, I might, since I'm not forgetting anything, I might not have a good amount of space available. So to that effect, one can actually make some approximations now and say, hey, can I do scaled gradient projection? So what is scaled gradient projection? It's again very similar to the GPM concept that I'm going to still try to learn in the orthogonal direction. But why not do this? I'm going to do a little bit of learning, if needed, in the old direction too. Okay? So in other words, I'm going to actually provide a factor lambda. In this particular case, if rather than M transpose, which was the gradient memory, I actually have M lambda M transpose now. So that lambda basically tells me that how much of that learning I can do in that old space. So if I do that, and of course I don't want to do, I want to make sure that the principal components, the important components of that learning in that direction is still maintained. But if I do a little bit of learning in that direction, and I call it a scale gradient projection, now I can actually do much better continual learning while still forgetting a little bit, but not that much of the old tasks. So I can still maintain good accuracy for the new tasks while maybe losing a little bit of the old tasks. So that's basically the scale gradient projection and can potentially do continual learning. Finally, one can also use, for example, what's called experience replay. So what we do in general, the humans in a lot of ways, we think of objects in our mind, and that reinforces our learning. So why not use the same concept here? So if I learn task 1, and then when I try to learn task 2, I keep a little bit of task 1. Maybe if it's images, I keep a few of the images of task 1. And then when I'm learning task 2, I actually use it in my learning. So to that effect, is it possible that I actually do have an episodic memory? I learn class 1 and class 2, and I keep a few of those data available so that if I were to have some other things that I have learned earlier, right, I can use that while I'm learning these cats and the class 1 and class 2. So I'm using basically an episodic memory, a few data from previous learning, so that I can actually reinforce what I had learned earlier. And that actually works pretty well. The unfortunate thing about that is that I have to keep a certain amount of memory or data available from the previous learning that I had. So can I do better? So one way of doing better is to basically reduce the memory complexity. It's not that I'm not going to keep the memory, but I'm going to reduce the memory complexity of continual learning, store only the important part of the image or important patches of the image in memory, and replay them to minimize forgetting. So in other words, rather than keeping the whole images, I'm going to keep certain important portions or patches of the image. If I can do that, then that turns out to be good. And by storing these important parts, how do you do that? There are different ways of figuring out, when I'm learning, which parts are important. And if I keep such information, it turns out that I can have a particular image with some of those patches. I can reduce the memory, and when I replay, I use these patched memory, which are much, much smaller, and use it for my learning. We can do different replays with image patches with zero padding, and performs really well with small memory. Just to give you an idea about how well it does, it shows basically for CFAR 10 and CUB 200 data sets with 20 different tasks, which are learned sequentially, and again showing for all these cases that this way of saliency-guided experience replay turns out actually does perform better with much lower memory requirement. All right, so changing gear once again a little bit, talking about again our bioplausibility. So far we have talked about neurons, synapses, we have talked about learning, and we have talked about different kinds of network architectures that can be used. So far we didn't spend much time on what kind of network architecture is important, other than the fact that it could be, for example, a spiking network for sequential tasks, LSTM for sequential tasks, or for that matter, we are going to be using, for example, standard deep learning network for image applications and so on, and for static applications. But one can do further and say, hey, is it possible that I look at, what kind of network architecture is used in the brain, right? Can I use such an architecture for my learning? Now, it's difficult to figure out what network architectures are there in the brain, but there's a good amount of work that has been done so far in the neuroscience community in understanding the visual cortex of, for example, the monkeys. The V1, V2, V3, IT of the visual cortex have been well studied for a long time. And the question, of course, is, hey, can I try to mimic the architecture of the visual cortex when I'm learning, for example, let's say images? So to that effect, there's been some very, very interesting experiments that are being done. The basic idea on some of these experiments is that what I'm showing at the bottom is basically a neural network, and in this particular case, a monkey, in this particular case, is shown a bunch of objects. And then the visual cortex is being probed. And you can't probe all the neurons. You probe a few of the neurons to figure out the activities of such neurons. And then you also have a standard deep learning network. Could be VGG16, could be a ResNet, and all these different networks, right? And so what you try to do is look at these input images that are shown to the monkey, and you're asking the monkey to recognize. You actually give a reward when they recognize something. You figure out the activities of the brain, and then at the same time, you try to look at the activities that you'd have in a standard, neural network like a VGG16 or a ResNet, and then try to basically say that, hey, is there a reasonable mapping between the activities that I'm getting in the measurements versus in my artificial neural network? And I try to combine them together into a V1, V2 region and so on. Now, it's a difficult task because I don't have that much data from different neurons, right? So using limited data, can I try to actually figure out what it is? And it turns out this work was done in DiCarlo's lab in MIT, and what they tried to figure out is that what's the correlation between this network architecture that I have versus the visual cortex? Is there a good match? Is there a bad match? If the match is good, does it mean the accuracy is better? Right? If the match is bad, does it mean the accuracy is worse? And what they found out is that kind of interesting is that if there's a good match between the activities of the brain versus the artificial neural network, then it's usually associated with a higher accuracy. Well, there are examples which it didn't work, but this was kind of interesting and a work towards really going in the right direction to be able to figure out what these network architectures are and how good today's neural networks are compared to what the brain does. So to that effect, there's something called a brain score that is available to determine sort of how your VGG16 or a VGG7 or a ResNet or, for example, any other network architecture that I have, how close it is to what the visual cortex does. There's still a long way to go, but it's an interesting approach to be able to figure out, hey, is there a good correlation between the activities in the brain versus the networks, and how does it relate to the accuracy?